Today we're going to work on what I consider the prettiest dynamic solution there is. So we have a block sitting on a hinged plank. The plank is raised until the block starts to slide. If the angle of the hill is theta, when the block begins to slide, what is the coefficient of friction between the block and the plank? So let's start by drawing a free body diagram. We have the gravitational force between the earth and the block pointing straight down. We have a normal force between the hill and the object coming out of the hill, and we have a friction force going up the hill. Again, we're assuming our motion would be down the hill. Now, since we have a block on a hill, we've learned from previous problems, it's very, very useful to create a coordinate system that has one direction. In this case, I'm going to call positive x down the hill, and another direction that comes out of the hill, so I'll call positive y out of the hill. Again, this is useful because it puts our normal force and our friction force in either x or y. We only have to break up the gravitational force, and also all of our motion in this case will be in the x direction, and there's no motion, no acceleration in the y direction. So it makes our life a little bit easier. It does mean, however, we have to break up our gravitational force into components. So we have Fgy, the y part of our gravitational force, and we have Fgx, which is the x piece. And if we know that the angle of the hill is theta, that means this top angle is also going to be theta. So Fgx will be Fg times the sine of theta. Fgy is Fg times the cosine of theta. If we now write our Newton's laws equations based on our block in the x direction, we have Fgx minus the force of friction, and that equals m times a in the x direction. And in the y direction, we have an equation that says the normal force minus the y piece of the gravitational force, Fgy, equals m times a in the y direction. And now, based on our problem, we can cancel a few things out. We set up our coordinate system so there is no acceleration in the y direction, so this becomes 0. We also know, due to the wording of the problem, it says this is just when the block begins to slide, so that's telling us that we can assume that the x acceleration is also 0. This allows us to find a few things. In the x direction, we got that the force of friction is equal to Fgx, which we already know is equal to, over here, Fg sine theta. And in the y direction, we know that the normal force is equal to Fgy, which is equal to, from our triangle here, Fg cosine theta. Now we have one equation left to use. We can use our model of simple friction that says that friction force equals mu times the normal force. We're looking for mu, the coefficient of friction. This becomes mu equals the friction force divided by the normal force. If we now substitute in our values for friction and the normal force, mu becomes Fg sine theta divided by Fg cosine theta. And now you can start to see why this is really my favorite and the prettiest dynamic solution there is. Our Fg's cancel out. We can use a trig identity and say it's sine theta over cosine theta equals tangent. So in the end, we get that our coefficient of friction mu is simply equal to the tangent of the angle of the hill, or the tangent of the angle that allows this block to start sliding downhill. So all this big mess we have in this problem reduces down to a very, very simple equation. It only depends on one thing. It only depends on the angle of the hill. That the coefficient of friction here, in this case, if we want to solve for it, doesn't depend on what planet you're on, doesn't depend on the gravitational constant, doesn't depend on your mass. It only depends on the angle of the hill. So again, a very, very pretty dynamic solution.